Alright, so we just finished talking about this staircase problem, and related to this problem is this sort of legend in mathematics that goes something like this. There was a student in a math class, and the instructor would ask questions, and the student kept answering the questions correctly, and the student also would occasionally correct the teacher, and so the teacher started to get really angry and started letting his ego get in the way, and so he decided to punish this student. And the punishment that he gave the student was that the student had to spend the rest of the day adding up all the numbers from 1 to 100. So the problem that the teacher gave the student was, do this sum, right? 1 plus 2 plus 3 all the way up to 100. Alright, so this is what the student had to do, and this was supposed to take the student all class. The teacher was surprised when the student came up with the correct answer just a few moments later. And so this is the legend, and the student's name was Gauss. So Gauss is this famous mathematician, and this is kind of a legend. Who knows if this thing is true, right? But legend has it that that's what happened. Anyway, you can see how this is related, hopefully, right? Because adding up all the numbers from 1 to 100, that's exactly what figure 100 is. But if you can change your perspective just a little bit and do this, like double the figure and then take half of that, right? Which is what we did here. It's like we described how many blocks were in each of these figures when we doubled the figure. That was easy to do. And then we just took half of that. And by doing that, you're able to come up with this formula for how many blocks are in figure n. And so finding the sum from 1 to 100 is not hard, right? You just plug in 100 to this formula. That's not exactly the way that Gauss thought of it, according to legend, right? So according to legend, Gauss's idea was a little bit different from this. And to kind of briefly introduce you to Gauss's reasoning, we're going to call this Gauss's method for finding this sum. So to briefly introduce you to Gauss's method, I actually want to start with maybe a smaller sum. So let's do the numbers 1 through 6. Now, of course, this you could do in your head pretty quickly and easily, probably. But I'm going to show you how Gauss figured this out. So adding up the numbers from 1 to 6. What Gauss noticed is that if you take this sum and you double it, but you rewrite the sum backwards like this, and then you add those up, what you get is 1 plus 6 is 7, and 2 plus 5 is 7, and 3 plus 4 is 7, wouldn't you know it? 4 plus 3 is 7. All of these things are just 7. You just get 7 a bunch of times. And how many times do you get 7? Well, you get 7. Well, you had 6 numbers to begin with, right? 1, 2, 3, 4, 5, 6. So you have this 6 times. So in other words, if you add all of this up, what you get is 7 times 6, right? Now, that's not the correct answer, right? 7 times 6 is 42. And if you add up 6 plus 5 plus 4 plus... what do we get? We get 6 plus 5 is 11, plus 4 is 15, plus 3 is 18, plus 2 is 20, plus 1 is 21. So if we do 7 times 6, that's 42. That's twice as much as what we actually need. Why is it twice as much? Well, because we didn't add up the original sum. We added up the original sum doubled. So to find the original sum, we need to take this number and divide it by 2. Okay? And anyway, so this is 42 over 2, which is 21, right? Which is the correct answer. So this was maybe not the best way to to express that, but anyway, that's the idea behind Gauss's method. So we could do the same thing for, say, 1 through 20. I'm not going to write out all of the numbers, but I might do something like that. So let's say that we wanted to find the sum of all of the numbers between 1 and 20. I suppose you could sit there with a calculator and do 1 plus 2 plus 3 plus 4 plus but if you didn't have a calculator, here's how you could do this using Gauss's method, right? So you do the same thing. You write this thing backwards. And then you add them up. And what you notice is that when you add them up, you get 21 and 21, and 18 plus 3 is 21, right? So you just get 21 a bunch of times. And the question is, how many times? Right? How many times are we adding 21 to itself? Right? How many times are we adding 21 to itself? Well, we had 20 numbers in the original sum, so we should have 20 numbers down here. So it looks like we're adding 21 to itself 20 times. So the original sum in black, right, this thing, should equal 21 times 20, but divided by 2. Because 21 times 20 is this sum doubled. So if we just want the original sum, then we need to divide it by 2. So there you go. Whatever that is, 20 times 20 is 400, plus another 20 would be 420. So you divide that by 2, I think you get 210. Oh man, that was just a coincidence that that it happened to be 10 times this sum. I didn't do that on purpose. Did I do the math right? Yeah, 420 divided by 2 is 210. Sure. Okay. Alright, so that's that idea. So we could do the same thing with just a general, well, maybe I'll go back to Gauss's problem now, right? Gauss's original problem. Right, you do the same thing for 100. It's 100 plus 99 plus 98. And this is how Gauss was able to get the answer so fast, right? That he did this little trick. And then you notice that you just get 101, 101, 101 a bunch of times. How many times? Well, there were 100 numbers in the original list. So this is going to equal 101 times 100 divided by 2. And that would still, without a calculator, that would still require you to do some work. But it's much quicker than having to add up all of these things. And actually not that much work, I guess. 100 times 100 is 1 with 4 zeros, so that's 10,000. And then plus 100 more would be 10,100. And then that divided by 2 would be 5,050. Right? So there you go. So you can do that sum pretty quickly. A couple things to say before I end the discussion for the day, and we'll talk a little bit more about Gauss's method next week as well, on Tuesday. Okay, but just as far as the discussion today is concerned, you can do this in general. You can say 1 plus 2 plus 3 plus n, right? What would you get? And maybe I'll do it like this. N minus 2 plus n minus 1 plus n, so that we have some numbers to work with. And if we use Gauss's method on this, here's what we get, right? We would add this sum up to itself backwards. So n, and then n minus 1, and then n minus 2, and then 3, 2, 1. And if we add this up, now what do we get? 1 plus n is just 1 plus n. I'm going to write it as n plus 1 though. 2 plus n minus 1. Well, if we combine our like terms, 2 minus 1 is 1. So this is again n plus 1. and 3 plus n minus 2. Well, 3 minus 2 is again 1, so this is n plus 1. And n minus 2 plus 3 is again n plus 1, and this is n plus 1, and this is obviously n plus 1. So you just get n plus 1 a bunch of times. How many times do you get n plus 1? Well, in your original list you had n numbers, so it must be n times. Okay, so you get n plus 1 times n divided by 2, right? n plus 1 times n divided by 2. Well, wouldn't you know it, that's exactly what we came up with here. Because notice that what we did to come up with this is we did visually exactly what Gauss did numerically here, right? We just took each figure, doubled it, right? That's what we're doing in blue, doubling it. And then, and then expressed how many blocks were in the doubled figure, right? That's what we're doing down here, okay? And then, to get the number of blocks in the original figure, we just divide the number of blocks in the doubled figure by 2. And that's what we're doing up here, right? So this is just exactly a visualization. This is just a visualization of exactly what Gauss is doing. And in fact, even if you look at the way the blocks are stacked, but they're stacked they're stacked upside down, right, on top of each other. Kind of like how when we write out the sum, when we write it down on the second line, we write it out backwards, right? So this is just a really good visualization of this numerical idea. Again, remember, I want you to understand both ways, okay? I want you to understand both ways. So this is not about finding the easier way for you. This is about you understanding both ways. I want you to understand both methods for solving this problem. But let me just say one last thing, okay? One last thing about this. Because your list might not start at 1, and that affects your sum, right? Let's say, for example, that instead of trying to find the sum from 1 to 100, maybe you want to find the sum from 5 to, I don't know, 34. Okay? So if you're trying to find the sum of the numbers from 5 to 34, you can still use Gauss's method, but you can't use this formula. The formula won't work for this because you're not starting right at 1. And actually you could use the formula, you just have to fix it up a little bit. We'll talk about that a little bit more on Tuesday. But let me just show you, as far as Gauss's method is concerned, you can still use Gauss's method, right? Notice if you rewrite this thing backwards, what would this be? 7, 6, and 5. Okay. When you add these up, you do still get the same number over and over and over again. You get 39 plus 39 plus 39 plus 39. Right? So you're still getting the same number over and over and over again. The challenge is to figure out, well, how many numbers do we have though? Right? How many times? So how many times? It's not 34 times because your sum didn't start at 1, right? You're missing 4 numbers, right? You're missing the numbers 1, 2, 3, and 4. But that kind of gives you a clue, doesn't it? Because if this did start at 1, then you would have 34 numbers on your original list. But you're missing the first 4. So really the number of numbers on this list is 34 minus 4. So it's really 30 numbers, right? It's really 30 times, okay? It's really 30 times. So, so this is going to be 30 times 39. And again, we doubled the sum, so we need to divide by 2 to find the original sum. I don't know how much that is, but that's the idea, okay? So, I think that's all I'm going to say for now. We're going to come back to this idea like I said, we're going to come back to this idea on Tuesday. But if your list doesn't start right at 1, just remember that when you're counting up the number of numbers on the list, you need to subtract off the first several, okay? So you need to subtract off the first several. Let me say this also. A big caveat, like a big problem that students often make, a big mistake students often make, is they'll do 34 minus 5 to find the number of numbers. 34 minus 5 is 29, which is not correct. So you don't want to subtract off 5, you want to subtract off the number that comes right before that one, right? You want to subtract off the first 4 numbers, right, to get you 30. Okay, that's all I have to say about this idea for now. We'll come back to this on Tuesday next week.